Thank you, Oliver. Next, we welcome Ben Stopford, lead technologist at Confluent. He runs the office of the CTO there, amongst other responsibilities, a Kafka engineer who's helped with the Kafka replication protocol, author of the O'Reilly book, Designing Event-Driven Systems, and a well-known thought leader in the industry on event-driven systems in general. The title of today's talk is A Data Mesh of Streams, where Ben will explore using event streams to build a data mesh and what the event streams would look like, why you'd want to, the pros of that approach and the cons based on the experience that Ben brings to the table. So we welcome Ben to the virtual stage. Thank you so much.
Hi, my name's Ben Stopford. I'm the lead technologist at Confluent. And today I'm going to talk to you about a data mesh of streams. So this is really a talk about the implementation of a data mesh using event streaming technologies, so Kafka, or you could also apply this to other things like Kinesis, etc., etc. I work at Confluent, so there's definitely a Kafka bias to this talk. But I actually think that Kafka and more importantly Confluent is by far the best platform to build this kind of stuff. So it's a great way for you to learn no matter what technology stack you're using, because you're seeing like the most advanced implementation. But I'm not just going to talk about the implementation itself. I'm also going to talk a bit about why we want to use data mesh in the first place and why streams are an important artifact of that. And my interest in this actually goes back a really long way. I've been working on the problem of trying to organize data in companies for about 15 years. It's been a real kind of mission for me. It's something that I am been really fascinated by. And the most frustrating thing actually for the first sort of 5 or 8 years of that was that people don't actually talk about this problem very much. If you look, you can't really find books on it. I mean, there are some books on data architecture, but they're not really pushing pushing the boundaries of what we can do next. And if you compare that to software engineering or software architecture, which has a whole wealth of literature written about it, disciplines that have been brought up to make the to kind of allow us to be more mature in the way that we build software and software architectures. Because we don't really have that with data, it's really important that we actually take the time to think about these things. And that's one of the things I love about data meshes. It's got people talking about this subject of how do we organize data in companies, so in a way that actually allows us to have kind of sane systems. And most importantly, because this is the most important part of it, is how those data systems evolve over time when they're all connected to one another. And that's a really interesting, but actually very hard problem. So today we're going to talk about that problem and its manifestation using event streams. So there are a couple of core influences around the whole database concept. There's actually many, but the two big ones for me are microservices, and that's because that was the first time we really shifted software architecture from the sort of monolithic centralized approach to this decentralized approach. You could argue SOA was the first incarnation of that. If you take that approach, which I do, microservices is kind of SOA done right. We're seeing the same thing here with data mesh. It's the first time that we've moved away from that centralized data warehouse-based approach to something that's decentralized and is spread around a company and is self-service. So data marts are another much older pattern that have some similarities because they were also about trying to sort of decentralize the data inside a warehouse. So it had specific materialized views in different databases that are specific to different parts of the company. It's actually a very different pattern, but a lot of the reasons that people built data marts were to solve exactly these types of problems. So when we talk about, Zhamak talks about the 4 principles, which she talked about earlier. I'm not going to go into those in detail because she's obviously covered those pretty well. I like to break them down into 2 categories: the socio-technical ones, which are like the first 2, and then there are these operational ones, which are the second one. So the first 2 are more about how we organize ourselves, and the second 2 are more about properties of the technology that make that work. And the parallels here with microservices, I think, actually are really important. So if you think about most microservice architectures, and actually a lot of the SOA ones that preceded them, they didn't work very well. And they didn't really work very well because we didn't have the practices or the tooling necessary to make that possible. And so what do? Well, we develop DevOps. Like DevOps is actually, the core underlying practices and technology which make microservices possible. They kind of give you these fast feedback loops that allow you to sort of move quickly, allow you to manage the complexity of many moving parts in a decentralized architecture. So, because without that, you're actually probably better off in many ways with a monolith, because at least it's simple, at least it's easy to change that one thing, even if maybe lots of people have to change it. So we have exactly the same parallels in the data mesh architecture, right? So because we are moving away from this monolithic approach where we have a data warehouse at the sort of heart center or at the back of a company to something that's decentralized where data is moving to many different parts, we need some principles, both socio-technical and operational, which are going to actually allow that process to work, because it's harder. It's harder to be decentralized. Always harder. So the socio-technical ones are more around how we organize ourselves. The operational ones are more about those kind of feedback loops and basically ensuring that all of the extra diversity isn't going to cause problems that are going to mean that the mesh fails. So, for example, self-service is about meaning that you can get your data very quickly. You need that because if you can't iterate fast, then the mesh can't evolve fast enough and it kind of falls apart. Likewise, the federated governance is because it's sort of the same thing. You need some processes and some technology which allows this distributed mesh to actually be a workable federation. And that was not the case if you don't have some principles and some technology to back that up. So firstly, before we get to all that, you need to work out whether or not you need a mesh in the first place. Don't build one just because they're cool. It's just like microservices, pick a use case which suits it. It isn't for everyone in exactly the same way that the monolith is a great pattern for many architectures. You shouldn't always use microservices. Likewise, data warehouse is a great pattern for many architectures. You shouldn't always use a data mesh. The time when you want to use a data mesh is where you've got a big complex company. And this will actually become very apparent as we go through the implementation. If your company spans different regions, different cloud providers, if it's got many different departments, that's the sort of area where a data mesh is actually a really, really powerful pattern, because it would be very hard for you all to coordinate around one data warehouse. If you're a little startup, probably don't want a data mesh. It's going to be overkill. So let's say you've decided you do want one. What kind of data mesh do you want? Well, there are, broadly speaking, two types. You can have a virtual mesh or a physical mesh. Physical mesh is one where the data physically moves to the destination data product. So like you can imagine, it's like, if you're building some reports, the data would move to you. You then have total autonomy over that data. It's basically your data at this point. There's a bunch of mechanisms which ensure you can stay in sync, but effectively you have total autonomy in the same way that in microservices, you have total autonomy. There's a kind of halfway house, which is to do with the data virtualization approach. In that, the data, it moves, but ownership doesn't move. So the data sits in place in the various different databases, and the virtualization technology runs distributed queries across the various different databases, the various different data products in those source systems. Operationally, there's a sort of big pro and con. The data virtualization approach gives you less autonomy because you don't actually have a physical copy of the data. It makes it harder to do things like stretching across geographical regions or across cloud providers. And it also has some kind of performance implications which make it tricky. So often what happens is that team that manages the actual data virtualization product can have a hard time making it all work. But it does have a great advantage, which is that it's actually pretty easy to set up. Like you've got these databases, you can put this layer over the top. It all kind of works quite quickly. With event streaming, you actually have to set up and move the data around. So you have to have you actually have to have those kind of physical copies. There's more to it than that. The argument is more subtle, and this is not what this talk it really is about. But primarily for the larger, this fully centralized, fully decentralized approach that you get with event streams, you're getting better autonomy, much more like microservices. You get to do what you want. You get to all of the degrees of freedom that organization needs. The virtualization approach is kind of like halfway house between a data warehouse and a decentralized approach. So let's talk event streams. I'm going to go through 10 steps. I'm going to go through them pretty quick. But these are the 10 the 10 canonical steps that you need to go through to build an event streaming system, a mesh that is based on event streaming. What do we have? Number one, we need to nominate data owners and create an environment. This is one of the socio-technical ones, where we fix at source. So the heart, we talk a lot about data products, but the heart of getting this kind of architecture right, so a data mesh based on event streams, is actually being able to fix at source. This is a principle that goes way back beyond the data mesh times. But if you can fix at source, you're in a wonderful, wonderful place. So let's take a practical example. In this example here, we have Alice. Alice is working on this order service, which is up in the top left there. And we have Joe down in this inventory system down at the bottom. And yeah, it's kind of a bit tricky for Joe. He's like getting this data and he hits a problem. He's like, well, what do I do? Well, his first option, like the data's bust. There's like some weird fields coming in. He's getting like errors coming out of his system. So what does he do? Well, there's a few things he can do. The first thing he can do is basically fix it up locally. That's the simplest thing to do. He's just gonna, make the data good. Assume you can get it. He'll fix it up. A little bit of software that does that transformation, and he kind of goes on. The other option is he could go back to Alice and say, look, can you fix this for me because it's broken? There's obviously some advantages to going back to Alice. Right, one of the advantages is if he fixes it at source, then everyone gets those benefits. But there's a subtler problem, which is if he starts fixing up stuff downstream in his data product or in his system effectively, then what happens is he actually starts to couple or be dependent upon the broken data. So when that data actually gets fixed, he often then has to make a software change, or he actually might also break. So you kind of get these very complex relationships if you're not able to implement a sort of fix at source. You can fix a source, though. For that to work, you have to be able to iterate very, very quickly. Like Joe is not gonna, he is gonna fix it himself if he can't get Alice to make progress quickly, and that's the crux of getting this bit right. Right, you have to have the processes and you have to have the technology that allows Joe to be able to get fixes from Alice. Alice has to have like SLAs. Alice has to behave like she is actually a data product owner. So when we look at this type of implementation, where we have Alice, the most important thing is that she actually defines herself as a data product owner. That's to say she takes responsibility for it. It's like that is, the definition of her job. She is a product owner in the company and the data is her product. Now, that's actually often a difficult thing for these people to do because that's not what they're employed for. They're employed to build some, trading system, or maybe it's a risk system, or maybe it's something that, suggests friends to people on the website. It doesn't really matter what it is. It's probably not to be a data provisioner. So you have to get that kind of organizational construct in place. And then you also need some technology to make it work, right? So, Joe needs to know where the data came from, right? How does he know where Alice is? So you need something like a catalog. We'll talk about that later. Something like data discovery with a Lineage tool that allows you to work out the flow of where different data sets come from. Because often data sets also come from multiple places. Like if you're looking at something like customer data, that frequently doesn't come from one place. It comes from many, many different data products that are in a big company, because you have like lots of different customers in different parts of the company. So that's number one. We want to make sure that we fix a source and we have the mechanisms in place to allow allow our data products to be owned responsibly. Number two, we want to introduce governance process to help teams interact. This is kind of linked to the first one. It's pretty simple in concept, but actually there's a lot of richness here in a bigger organization. So you have to think about how data products are going to be published inside the mesh. Like how does, is there a quality bar? You have to think about the schemas. Are you going to define these schemas up front? That tends not to work so well. So you have to have them to evolve, because that's probably the only practical solution, is to have evolution of your schemas inside the mesh. So what are those kind of minimum requirements for the data? What are the minimum requirements for fixing it up, right? So what happens if something's broken? What are the SLAs that a data product provides the rest of the organization in terms of how quickly they're going to be able to address and fix problems? And it's not going to be, be waiting like months for something to get fixed. It's likewise for uptime, etc. And then also what happens when schemas change? Like how's that going to happen? We'll talk a bit about how that works in event streaming in one of the later points. So that tells us a little bit more about how to kind of organize ourselves. Now I want to talk about a bit about how we build these things. So how do we build a data mesh with event streams? First thing, number three, let's create the right streaming infrastructure. So data in an event streaming data mesh, the data products are actually event streams. And that's actually, even if you've got like a database and there's like a CDC process that's taking data out of the database and publishing it to the mesh, the manifestation of the data product to everybody else in the organization is actually the event stream. The only time that actually really gets broken is when you have some source which is not an event stream, like some legacy system, which is always going to happen, by the way, because we very rarely start from scratch with these kind of things, because they're patterns that are suited to existing complex architectures. So you're always going to have some of that as well. Talk a bit about that later. But the key point here is that data products are going to be your event streams. That's your foundation. Next, you need some way to quickly get data out of a whole variety of different systems. This is where you want out-of-the-box connectivity. So it could be pulling a data source like Salesforce information directly into the mesh. It could be CDCing from something like Oracle. You want to have these kind of connectors. If you're using an event streaming system, for example, Confluent, but there are others, then you get like a wealth of these connectors. It's like, I think more than 100 connectors in Confluent, which are just there for you to pick up and use and integrate with a variety of different sources. So you can get data into the mesh quickly, and you can get data out of the mesh quickly, because there are connectors on both sides. The next thing you need Kafka or Confluent, or some event streaming system. You need connectors that allow you to create these endpoints around the mesh. And then finally, you need some mechanism of doing transformation and discovering what data is actually, reading data from the mesh. In an event streaming system, that's done by something like KSQLDB. So KSQLDB is an event streaming database, and it has two core functions in this regard. Firstly, is it allows you to join and transform data, almost like a kind of real-time ETL, and get it out of the mesh. So we can transform something into a bunch of different data products, join them together, maybe aggregate them, and present them as a new data product, which we're going to use inside our system. So we're going to put it maybe in BigQuery and do some queries on it there, whatever it is that we want to do. And that's a wonderful thing about an event streaming data mesh. It's entirely up to us. We can use whatever technology we want, because we're just pulling data out and then we own it. The other great thing that KSQLDB does, which you do need some implementation on, is if you're not going down that route, you can actually just query the mesh directly. And this is actually pretty useful or pretty important for debugging reasons, and also just for trying to work out what's going on. So KSQLDB will allow you to materialize a view based on a piece of SQL, which brings together data from a set of different data products, and you can just query that in real time. relatively simplistic query interface if you compare it with, let's say, like a very rich data warehousing tool, but it's functional enough for these kind of queries. Number 4, make schemas the contract for your data products. You have to have schemas, right? If you're in a mesh, in exactly the same way that APIs or schemas are the contract that sits between microservices, you need schemas which are going to be the contract between different products inside the data mesh. So how does that work? Well, we use something like a schema registry. I mean, Confluent provides one of these. Again, there are other people that provide them. This is a repository for where you can put your schemas for runtime access. So different pieces of software around the organization can automatically read a schema of a specific version from the schema registry and and validate whether or not data. This is how you validate the data that's going in to make sure it complies to that schema. And this is how the various different teams which are reading from the data mesh are able to ensure or program against an interface that they know is going to be upheld. So schemas, in Confluent's case, they actually come in 3 different formats. You've got Avro, Protobuf, and JSON schema. And they can be used with, but you can also, the nice thing about them is it's actually not, there's nothing like sort of Confluent or Kafka specific about the schema registry. You can use these schemas on anything. And actually, when we talk about like the cataloging and the ability to tag these schemas and manipulate them and permission them and all that kind of stuff, that actually works regardless of whether or not it's actually backed by a topic. So let's say that you actually have some batch files which really represent another data product, it's a legacy system. You can still wrap those, have those governed by a schema, and then all of the tooling, all of the user interface, all of the permission that you're going to use inside the mesh, that actually can also then make use of this non-event stream based data source. So you can mix these things together, streams and non-stream based data products using a single schema registry, which is actually pretty cool. So you've got your schemas in place. You've got these APIs for your data mesh. They're in place. They're available at runtime. You probably actually also need to have them stored somewhere. GitHub's a good place to do that. But then you need to work out, well, how they're going to change. So let's say you do put them in GitHub. A great way to actually manage change is a PR process. So let's say you propose a change to a field which is non-backwardly compatible. You would then get a set of reviewers from the various different parts of the organization that are interested in that particular data set. And the really nice thing about that is that you can start programming against that interface whilst that whole programming against that PR for that schema change whilst that whole validation process is happening. You might have to make some changes because other people would have feedback, but you can make progress quickly. But planning for schema change is actually really, really important. And when we say that, there's really like 2 types. There's like, these different formats. Avro in particular supports backwards compatibility, so does Protobuf to a certain extent. That's enough for many changes, but you always end up in this situation where there's going to be an incompatible change. And what that really means is that you're going to have, if you publish that new schema version and somebody upgrades to it, their software is going to break. They have to go and make a programmatic change to their ETL jobs or whatever it might be to ensure that they're not going to break when you release this change from your data products. The way that we do this with event streams is this rolling upgrade window. So you basically you've got 2 schemas, the old schema and the new schema, which is incompatible. You basically publish both for a period of time. And you say, right, we're going to publish both for like a month. Guys, you need to move after a month. The old one's going away. So you have that kind of like rolling window. Gives people time to upgrade. Number 6, we need to catalog our data products, right? You need some way to kind of find them, and you need some user interface that's actually going to serve them, allow you to search them. So answering the question, how do I find out what data products are available in my, what data is available in my company, and how do I build these? How do I get these into my own system? Two core ways of doing it with event streams. Firstly, we need to attach metadata to schemas or topics, right? So we have to be able to maybe flag it as being sort of PII compliant. We might want to talk about where the author came from. There's like a whole bunch of metadata. And it's a very good thing in an organization to be prescriptive about the way that you do this, so everybody does it in a standardized way. A good way to do this is by standardizing the user interface or the software that actually does that tagging of these different data sets. And going back to that bit of governance that we were talking about before, where there is an entry requirement to being a data product, to being part of the mesh. And part of that would be you have set up these various different pieces of mandatory metadata. So you've got metadata attached to your schemas or your topics. And next you need some central way of searching it. So you can do both of these things in Confluent Cloud. Actually, these are both pictures from Confluent, screenshots from Confluent Cloud. You can attach metadata tag different schemas with a variety of different, any metadata you want. And you can then search by it using a simple search tool. So here we're looking at different schemas inside the mesh, different topics inside the mesh, simply with a sort of Google-like search from a central API. So that's just like straight out of Confluent Cloud. Okay, number 7, let's make the mesh self-service using event storage. So that feedback element is so important. If you think back to Bob and Alice, it's Bill and Alice, wasn't it? Bill and Alice. If Bill needs to make that change, or Bob needs to make that change, or whatever it was, Alice needs to have an SLA, but also Bill needs to be able to he needs to be able to get those changes fast. And often he'll need the whole kind of data set. So you don't want to be dependent on what Alice is doing in order to necessarily just get access to a data set. Likewise, if you're starting something fresh, it's got to be self-service, because that ability for a mesh to be able to create new data products, new materialized views, so instantaneously, that's what actually makes it work. If you have to go through some protracted process, then the whole thing kind of grinds to a halt, and people find, teams tend to find other ways of solving problems. So the way we make the mesh self-service is basically by using Kafka's ability to store data. So Kafka can store data in theory indefinitely, but you're basically limited by the disk on a certain machine. That isn't a problem for most people. If you use something like Confluent Cloud, you get infinite storage by default. So you get like price efficient storage, and you can store as much data in there as you want. So what that really means is if you've got like some customer data, for example, and you put it inside the mesh, it can just live inside the data mesh. Kafka and Confluent both have this thing called a compacted topic, which actually means that thing doesn't grow indefinitely. It just grows based on the data size. So if you have this event-based representation, which is like every single change, which is how event streaming systems work. So you've got all the different deltas. A compacted topic will basically summarize those up. So you have something that looks more like a table, which makes it very easy for you to get that data out. So what this really comes down to is you want to have some way of getting the whole data set, but you also want some way of having that data set be kept up to date. Kind of two ways you can do this really. One is with Kafka. The second one is some kind of API interface where the data product source provides you with that service. That's also applicable. So basically maybe have like an API, we say, just give me it all again. And they have to provide a feed of that, a stream of that data, the back population data to you, kind of snapshot. The reason that storing data in Kafka is often easier is that it takes the burden off a lot of these source data products. So if you think about Alice, Alice, you don't want to put like too much responsibility on her. It's much easier if the infrastructure is taking care of storing, let's say, the customer information and providing it on demand as a full data set, as well as keeping it up to date. And you can do that with event streaming systems. They're perfect for that. So number 8, don't limit yourself to a single cluster. So I think a lot of people, when they sort of think about, an event streaming system, they sort of think about having like, this centralized Kafka cluster that everything goes through. In practice, that actually tends not to be the case. People tend to have multiple clusters, and actually, this is changing hugely with the introduction of cloud products, because on the cloud, a cluster is kind of free. It's like it's a relatively cheap entity, or at least certainly if you're using Confluent Cloud, because it's a service implementation of an event streaming system like Kafka. Then yeah, you can actually have many different clusters. The cost of the cluster, you're just paying for what you use. So you can have a whole bunch of different clusters in different places. If they're not doing anything, they're not going to cost you anything. And you also have these like very advanced ways these days of linking different clusters together. So, for example, in our case, Kafka has like a sort of proxy-based approach called Mirror Maker for moving data between different clusters. So you have like a separate process, and the data kind of gets pulled out and then pushed into the other cluster. Whereas Confluent has a much more advanced approach where you have like two clusters and they have an internal replication protocol, and basically the same internal replication protocol is used to connect these two things together at the same level. So they're like almost like one Uber cluster, but they're like a little bit dissociated from one another. And the great thing about that is because they're a bit dissociated, you can put these clusters around the world. So you can have them in different cloud providers, you can have them in different geographical locations, and you can create like a sort of a cluster of clusters, which is a very advantageous if you're a big company. Many data mesh users are actually big companies, and you want to be able to build something that spans the globe or those different providers. If you do this, you have these more complex architectures with multiple clusters. Some of them could be really, really small pay-as-you-go ones. Others could be massive, hulking, physical, dedicated environments that are doing super high throughput. But you're always going to need this. It goes back to this mechanism we talked about before. We're going to need some kind of data lineage tool, which is going to let us figure out where stuff came from. Like if we've got a problem with this data, where did it come from? Easy if it's just one source, but often in a mesh, you've got many of these little data products, and the thing that you're actually using sews many of them together. So how do you trace that back? That's where you need a data lineage tool, like the ones we were discussing before on Confluent Cloud. Number 9, secure everything. This sort of kind of goes without saying. You want to have a bunch of security features inside your mesh. You need to be able to permission that at a very fine level of granularity. So access to event streams need to be permissioned by some kind of central body. You're going to have some process around that, some kind of way for people to obviously get validated. You also need to have the technology. The mesh needs to implement that underlying security layer. So Kafka does this with ACLs, which are functional and allow you to make progress with this problem. Confluent has something that's a bit richer. So you have a role-based access control, various different cloud integrations, etc. So you can do much richer and UI-based permissioning. Finally, number 10, we're at the end of our list. Build on what exists already. And what exists already for in this space is Confluent Cloud also provides a lot of these features which help you build a mesh. It's got obviously Kafka, Schema Registry, KSQL DB are all ready for you. All of those connectors which allow you to connect to your various different databases, because quite often you want to use your database, whatever it might be. So you can connect these different pieces together inside the mesh using a cloud product like that. But actually to implement a mesh, you need another thing on top, because you actually have to think in terms of data products, and you have to think in terms of the various different governance processes that you've defined in your organization, which is going to make it work for you. So you kind of need a layer on top. So we had a go at that. Adam Belmer here built a prototype around what a data mesh would look like. It's relatively simplistic, but it grabs most of the core details of that. And the great thing about this is there's an example of it running on the internet. You can just go and have a look at it. It's only a demo, it doesn't have all the functionality, but all the functionality is available in GitHub, so you can go and check this out yourself. So what I'm actually going to do is I'm going to do a very, very brief demo of this actually just the one that's running on the internet itself. So I'm going to bring this over here, and there we go. So this is the demo. Hopefully this is actually working. This is the demo of the data mesh product itself. So what's happening here, I have to look away from the camera for this bit. What's actually happening here is, this is just the home screen. We can explore a variety of different data products inside this prototype. So this prototype is sitting over on top of Confluent Cloud. Confluent Cloud is actually providing all of the features. This is just kind of sitting over the top and providing an abstraction which is data mesh specific. So here we can discover different data products, right? So we can see, we can search, search for different types of data products. We can see their schemas. We can see a bit of the metadata, which is been logged against them. So here we got name, there's a domain, there's a kind of owning team. There's there's like a quality indicator. These are just things that you would define yourself in your organization and put into as metadata on your mesh that you can then sort of see these various different pieces. And we can search all this stuff just using the search features inside Confluent Cloud. So the APIs here are actually just hitting the API, because obviously in Confluent Cloud there's a GUI, but there's also an API which you can hit, so you can build your own mesh, which is exactly what this is doing. And actually, if we look at this little audit log, we can see, you know, we've got all the subjects from the data catalog inside Confluent Cloud, et cetera, et cetera. So we have this catalog of all of the data inside our mesh. We can search it right here. We can also look at things like data lineage. This doesn't go through to Confluent Cloud because it's just a demo version, but if it did, you'd be able to see the actual data lineage graph. A few other bits that are good to see. We can export this data product if we want to. We can then also start creating applications which are extracting data from the mesh. So let's say we've got some stock trades here. Again, we can then look in and we can build a KSQL script. So this is a piece of SQL, streaming SQL, which is going to pull together a variety of different data products, join them together, and then we can apply some kind of transformation, simple transformation, or we can do some pretty complex aggregations. So we can do kind of basic ETL right through to complex stream processing all inside here. And then you can actually just here in the product, we would just execute this statement. That's actually running against Confluent Cloud. Again, we can see this inside the log. That actually creates a new data product. Well, so we can see this now. We've created this new data product, which is popped up here, and we can decide whether or not we want to add that to the mesh, because it might just be something intermediary, or we might want to publish it to the mesh so that other people can see it, in which case we obviously need to fill in all the metadata and that kind of stuff as well. So you can basically, in this thing, you have a bunch of just simple code, a simple user interface that sits on top of Confluent Cloud. Confluent Cloud is running in the background. Confluent Cloud is providing the search, the cataloging, obviously all of the underlying technology. And this is just a way of piecing those different pieces together in a way that's actually data mesh-like and gives you that central mechanism, that central port through which you can manage and allow people to collaborate around something that really is, looks like and behaves like a data mesh. Cool. So that's effectively the end of this talk. These are the 10 principles: nominate data owners and create environments where Fixat source works, introduce governance to your processes and help teams interact, create the right streaming infrastructure. Obviously, you need the technology that backs it up, and our cloud products, as well as many others, I think, are good backings for that. But it's you need to make use of schemas as a contract for your products. You want to plan for schema change. You want to have some kind of data catalog, somewhere that you can store all of the metadata that you need to define all of the many attributes that you have of your data inside the mesh. You want to make the mesh self-service with event storage so that you can spin up a new project and immediately get access to all the data that you need. Don't limit yourself to a single cluster. Secure everything and build on existing technology if you can, because it makes life easier. And that is all I had to say. Thank you very much. I'm sorry if I went a little bit over time. I'll be very, very happy to answer any questions that anybody has, whether it's about data mesh, whether it's about event streaming. And thank you for attending and taking this time. I really enjoyed being here. Thank you.